In this video, I want to make some considerations on the so-called energy momentum tensor. In particular, we start from a Lagrangian density, which depends on a field phi. In principle, you might also add a subscript here, for example, phi alpha, to denote the fact that there can be more than one field. But this can be easily generalized, and since it can be easily generalized, I just want to consider one field for the sake of convenience without writing down too many subscripts. And apart from the field phi, the Lagrangian density can also depend on the derivatives d alpha phi. So when I write this, I mean the derivative of phi with respect to the coordinates x alpha. And we are in special relativity, so when we want to write down an action, we have to integrate the Lagrangian density over the four coordinates d4x. So integral Lagrangian density d4x. By taking the variation of the action and setting it equal to 0, what we get is, of course, a set of equations, which are Lagrange equations, and they can be written like this, in this form. So we have the d mu, the derivative d mu of the derivative of the Lagrangian density with respect to the derivative d mu phi, minus the derivative of the Lagrangian density with respect to the field phi equal to 0. Now, these are Lagrange equations, but notice that we can make use of a symmetry of the Lagrangian density. It's quite easy to see that if we take the derivative of the Lagrangian density with respect to the coordinates x mu, we can see that the result is 0, because the Lagrangian density does not depend explicitly on the coordinates. It's an assumption. So one possibility is, of course, dl dx0 equal to 0, where this x0 is the coordinate related to time, so it's proportional to the coordinate related to time. So it's like taking the derivative with respect to time of the Lagrangian density. And by doing so, one can obtain also a conservation with respect to time, which gives rise to the Hamiltonian density. In this case, I want to be a little bit more general by writing down the derivative with respect to x mu, because in general you can see that the Lagrangian density does not depend explicitly either on time or on the spatial coordinates x1, x2, x3, or if you want x, y, z, the three dimensions related to space. Now, if we rewrite this, we can say, okay, this is the derivative which must be set equal to 0, but it can also be rewritten in the following fashion. So the Lagrangian density depends on the field phi, so we can apply a chain rule, and it also depends on the derivative. So here we have d alpha phi, d alpha phi, but we take the derivative with respect to x mu. This remains, of course, equal to dl dx mu. Now, for the sake of convenience, let's just rewrite this partial derivatives with respect to the coordinates as, in their abbreviated form. So in this case, we have d mu, whereas in this case, I can replace this with, of course, d mu, and similarly here we have dl d mu, like this. Now, another thing that you want to notice is that the order of the partial derivatives here can also be swapped, so we can write d alpha d mu. And then we can also use Euler-Lagrange equations to rewrite this partial derivative, which appears here, as this partial derivative here, because they are equal. So we can put an equal sign here and erase this equal to 0. And let me change this mu, which is a dummy index, to alpha for the sake of convenience. And I want to replace this partial derivative, which is this one, with this. So when we apply this equation in here to replace this term, we get d alpha, dl, d alpha phi, d mu phi plus dl, d alpha phi, d alpha, d mu phi equal to d mu l. At this point, you can notice that here we have a product rule for the derivative because we can rewrite this as d alpha of dl d alpha phi multiplied by d mu phi. You can see that if you apply the product rule for the derivative, you have to take the derivative of the first term multiplied by the second term, which is this one not differentiated, and then you have the first term, which is this one, multiplied by the derivative with respect to alpha of d mu phi. So you can rewrite it like this. Then we can also rewrite this second term by changing this index mu, and therefore we have to use in principle we have the Minkowski metric because we are in four-dimensional space-time. But since we have mixed indices, one is an upper index and the other one is a lower index, I mean, I have to write this as delta alpha mu. The mixed tensor, in particular the Lorentz metric tensor, era alpha mu, is equal to the Kronecker delta alpha mu. So we can simply write the Kronecker delta like this. It's like an identity matrix. If alpha is equal to mu, we get that the delta gives 1 and it gives 0 otherwise if alpha is not equal to mu. And then here we have L. So we can write the overall equation like this: d alpha, dl, d alpha phi, d mu phi minus delta alpha mu L equal to 0. Now we can define this to be a tensor with the mixed indices t alpha mu, and this tensor is none other than the energy momentum tensor. And this would be a conservation law because we have some kind of divergence of a tensor equal to 0. So this is the conservation law for the energy momentum tensor. And for example, if we set alpha and mu equal to 0, so we calculate t0, 0, we would have the derivative of the Lagrangian density with respect to d0 phi, which we can simply write as phi dot for convenience, multiplied by phi dot minus the Lagrangian density, because delta 0, 0, of course, would be equal to 1. And dl d phi dot is also sometimes is defined as the momentum density pi, which depends on the coordinates x alpha, or if you want, we can simply write pi of x. So T00 plays the role of the Hamiltonian density, and it can be written in this fashion. Whereas, if we, for example, evaluate T0i, we have dl derivative. So in this case, we have to set alpha equal to 0. So we have derivative with respect to phi dot of di phi, and this term would be 0 because we have that alpha is not equal to mu, so delta is 0 there. And this expression in particular is related to momentum. In particular, when you integrate t00, t00 over a certain volume, let me write it as dv, you get the Hamiltonian, because this is the Hamiltonian density. So this is capital H, whereas this is H written in italic. And on the other hand, if you integrate T0i over a certain volume, what you get is the ith coordinate of momentum. So this is just some intuition behind it, some useful mathematics, And this expression for momentum will also be used.